So hello again, everybody. My name is Martin Liira, and I'm coming from the Geological Survey of Estonia, where I work as a marine geologist, but also I'm a lecturer at the University of Tartu. Today I would like to say a couple of words about my passion, marine geology. And marine geology, but before that I would like to stress that for me as a geologist, Estonia has been always part of the Arctic. About 20,000 years ago, Estonia was covered with a glacier about maybe maximum about 1 kilometer thick, and after this glacier retreated from our land, it left new terrain in our land, and it's mainly modified by the glacier processes. And the same processes we can see happening now in Arctic regions are actually present here in Estonia also, like those plow marks, iceberg plow marks in the seabed sediments in the Barents Sea or in Baltic Sea. They principally are the same, only the age is different. So in a way, we are part of the Arctic, we are part of this large system. Marines, oceans and seas represent one of the main sinks of sediments eroded from onshore. So by layer, they kind of like preserve the past history. As shown here in an upper picture with a seismoacoustic profile of one sediment layers. So going deeper into these layers, we sort of go back in time and we can read what was the conditions, environmental conditions, atmospheric composition, pollution levels, and etc. during that time when those layers were deposited. This process is universal in accumulation basins around the world, in the Arctic basins, but also in the Baltic Sea, here we can see, for example, the heavy metal profiles in the Baltic Sea sediments, where by dating those sediment layers, we can go from nowadays back to the early last century, where we can see that during the 70s and 60s, where the pollution was very heavy in here in Baltic Sea countries, we have a maximum of toxic elements in our sediments. Later, when we agreed among us that we should take something up, we should do something about it, we agreed to reduce the pollution levels, and actually we can see that trend also present in our seabed sediments. So studying seabed sediments, it offers us a glimpse into the past histories. My journey into the Arctic started from this place. Many of you already know this is the University Center in Svalbard, where I had the honor to work together with Rico Normets. But to study Arctic is, as we well know, is very, very important, because Arctic is going through very rapid changes. One of the good examples how rapid and how strong these changes are, actually, if we look the extent of sea ice extent in the Arctic Ocean. Starting from mid-19th century up to nowadays, we can see that the maximum extent during the September month has been decreasing very rapidly, and the change is significant. Even if we look the shorter time span, such as the approximately last 50 years, the retreat of sea ice is absolutely evident. Although some years have better ice cover years and some are less good in terms of sea ice extent, the overall trend is quite clear. And it's quite clear that quite soon in the future we will have first summer in the Arctic Ocean where we don't have sea ice in the Arctic Ocean. And of course this is due to the global warming and the increase of greenhouse gases in the atmosphere. Just to remind you that this global warming is not universal. It's not the same everywhere in our Earth. But we have regions where the temperature increase from the previous is much larger compared to what it is in the rest of the world. Especially in the Arctic region where temperatures are increasing 4 times faster compared to the rest of the world. And this phenomenon, Arctic amplification, is due to different reasons. Of course, the increase in greenhouse gases concentrations, but also the decrease in albedo in Arctic region helps to amplify the temperatures in Arctic. If we talk about the greenhouse gases, of course, the main driver is CO2, but also methane is a very, very potent and very strong greenhouse gas, and its levels in our atmosphere are steadily increasing. Here in this graph shows couple of key things about methane in our atmosphere, where if we look at the northern hemisphere and southern hemisphere and the methane concentration in our atmosphere, we can see first of all in a timeline that those maximums are steadily increasing. But the most of the methane in our atmosphere is in the northern hemisphere, and it's not migrating to the southern hemisphere. There are several reasons. Of course, most of the land is on the northern hemisphere, but also in the tropical zones, the tropical zone effectively breaks down the methane molecules in our atmosphere, and so preventing methane to evenly distribute across our globe. Meaning that all the methane which is produced in northern hemisphere will stay here on northern hemisphere and increase the Arctic amplification in that region. There are many sources of methane. Of course, melting of or thawing of permafrost is a very big source of methane. And some other processes also producing a lot of methane there. But seabed sediments are also one of the sources of this potent greenhouse gas. Already in the mid-last century, when the seabed mapping started to use more developed technology, they started to notice that in the seabed sediments we can see here and there these small pits or craters, which can be quite large, up to a couple of hundred of meters, and be up to tens of meters of depth. These craters, they are called pockmarks. Sometimes they can occur in large clusters in a seabed where you should have a smooth and cozy and silent seabed. These craters or pits are believed to be kind of like a conduits of fluids seeping out from a seabed, and that's why creating these pockmarks. These fluids can be, of course, usual groundwater or meltwater or these kind of things, but also the overall warming of the Arctic destabilizes also the methane and other hydrocarbon gases in the lower levels of the seabed, and they start to migrate diffusively upwards, and in some cases creating these pits or craters. So it means that whenever we see these kind of pockmarks in our seabed, there's fair to ask, are those pockmarks still, what kind of fluids they are seeping? Is it a strong, do they contain strong greenhouse gas methane, or are they just at the moment inactive and not seeping the methane there? One of the most active systems in the Arctic, where sea and land come together and where most of the sedimentation occurs, are the different fjord systems in the Arctic regions. Arctic fjord systems like this one here, Eastfjord, also Maria talked about the biggest fjord system in West Spitsbergen Island, is very dynamic system, and one of the, and in general the key environment for the sediment accumulation and also related processes. This Eastfjord has been mapped very thoroughly by previous researchers, and during this mapping, the mappers discovered a lot of pockmarks, these craters or pits in seabed sediments, these yellow dots here. There were over 1,000 of these craters there, and it was believed to be an escape route of the hydrocarbon fluids. Especially considering that Svalbard has an active hydrocarbon system geologically linked to the Barents Sea oil and gas source rocks. So it was fair to ask, are those pockmarks still seeping out the strong methane gas from the seabed to the water column? And in shallow environments like in fjords, we can't rule out that some of the methane, if it's seeping to the water column, can escape the water column also to the atmosphere, and increasing the Arctic amplification even more. For that, we collected a lot of samples, a lot of coarse sediment samples. We measured the methane concentration in the system. Fortunately enough, at least for a global scale, we found the methane levels in those pockmarks are relatively low, indicating that at least in Eastfjorden system, those pockmarks are inactive. They are not seeping actively methane gas. Probably what happened was that the biggest gradient for the seeping of methane from the sediments happened just after the deglaciation, when the pressure drops in the systems were the highest, and probably the most of the methane were lost during glacial retreat. However, we have an indication that at least to some extent the seeping gas from these sediments are thermogenic in origin. It means that the same gas, basically the same gas we are exploiting from the Barents Sea oil and gas fields. However, like I said, fjords are dynamic systems, and the first basins where the sediments start to accumulate after the erosion from inland. So it's very important to understand what is happening in these fjord systems in terms of greenhouse gases, but also in terms of other components like nutrients or potential harmful components, and so etc. For example, phosphorus is an important nutrient for the life, but it's little is known about how climate change and increase in erosion from on land affects the phosphorus cycles in those fjord systems. And these fjord systems, due to climate change, are being extensively affected by this increase of erosion. And sediments, of course, affect what is happening in the sediments. Of course, this affects also what is happening in a water column. Just recently, we conducted research of 2 fjords north of Svalbard and next to New Ålesund, and also some shelf areas where we've collected samples, especially to study what is happening with the phosphorus and other nutrients in those systems. Not surprisingly, we could see that in the fjord systems, the organic carbon concentrations in the surface sediments are quite high, comparable to the open shelf sea sediments. A little bit surprisingly was that the level of nitrogens in the total nitrogen in the fjord system, but also in a shelf sea, are relatively little, indicating that the nitrogen could be having bigger effect to the local ecosystem. The lack of nitrogen could have a bigger effect to the local system. Increase from a fjord mouth from inland to outer part of the fjord, clear indication that closer to the glacier front, the organic carbon concentrations closer to the glaciers are relatively low and increase towards the outer part of the fjord. However, this is quite well known, but what is less known is how the phosphorus is acting in the fjord sediments. The story of phosphorus is a little longer. Usually we think about phosphorus as just one element in our system. But if we look more closely, we can actually divide this phosphorus in our sediment systems into the different categories. Mainly we can divide that phosphorus as immobile, inactive, these the yellowish bars here, or mobile and active. I mean mobile, that's the phosphorus forms which are useful for the ecosystems, which can diffuse back from a sediment to the water column and increase the bioproduction. These 2 stations here represent the typical seabed sediments where we have roughly half or more than half of the phosphorus in the sediments are immobile forms. They are not actively anymore related to the ecosystems. And we have maybe up to 40% of phosphorus which is mobile. And from this 40% of mobile phosphorus, majority of that is bound to the different iron minerals. Iron is usually the biggest fraction of the mobile phosphorus. However, if we go into the fjords, we can see that the phosphorus bound to the iron is the proportion is much less compared to the proportion of the most labile phosphorus form, which is very effectively diffuses back to the water column and can affect the bioproduction there. So indicating why is that? Probably this is related that the sedimentation rates are so big that even the diagenetic processes which convert the labile phosphorus from one form to the iron form are still not happening because the fresh materials are put on into the fjord system. How this system will act in the future needs very close attention, and probably we should do and more campaigns to see what is happening in these fjord systems. So this is ongoing research. Lastly, I would just say a couple of words. I would like to say thank you to my fellow members of Polar Club, and just to point out that, like Mario also said, it's very hard to do research in Arctic. It's very costly, and it's time-consuming, and due to the remoteness and other issues. And I was extremely lucky that I could collaborate with sailing yacht Admiral Bellingshausen crew on the Arctic voyage in 2021, where in a citizen science campaign, Maris and Tiit Pruuli were kind enough to collect me surface seawater samples from the exceptionally large area during the cruise on different. And I was able to study them and to see how many hydrocarbon gases, methane especially, are there in those water layers. Fortunately enough, everything was normal, and we couldn't detect any higher levels of methane gas in the water column, which in a way is a good news. However, just that was a couple of glimpses into the sea sediments and why they are important. And believe me, they are very important. Thank you. Are there any questions? Maybe one? Oh dear, I used all my time. Sorry for